Hello everyone. Today let's learn about the BIER technology. BIER, short for Bit Index Explicit Replication, BIER, is a new multicast technology. Before we discuss the technology, let's briefly review the development process of multicast technologies, which includes 3 phases. The first phase is the PIM phase. PIM is the most basic, widely deployed and used multicast routing protocol, which can be deployed provided that a unicast IGP is available. The second phase is the P2MP MVPN phase. The P2MP MVPN technology was introduced to meet multicast service deployment requirements in L3 VPN scenarios, and it extends L3 VPN, LDP, and RSVP technologies. The third phase is the BIER phase. BIER and segment routing have similar fundamentals. Specifically, in segment routing, a network path is divided into segments, and a segment ID is allocated to each segment and forwarding node. In BIER, a bit position is allocated to each ingress and egress, and the forwarding plane replicates and forwards multicast messages based on bit position information. Multicast and unicast technologies develop together, with the latter playing an important role in promoting the development of the former. Now, let's discuss the background of BIER. BIER was developed because traditional multicast technologies, such as PIM, cannot meet the requirements of rapid multicast development. Traditional multicast technologies face the following challenges. First, they require a multicast distribution tree, MDT, to be established for each multicast flow. If numerous multicast flows exist on a network, devices will be overloaded in maintaining multicast entries. Second, if traditional multicast technologies are used, the overlay and underlay networks will be deeply coupled. If a network fault occurs, multicast service convergence takes place only after IGP convergence completes, slowing down end-to-end service convergence. Third, when a new user joins a multicast group, its join requests must be sent hop by hop based on the MDT. When the network scale and the number of hops on the MDT are both large, end-to-end convergence will be slow, and therefore unable to meet the requirements of multicast users for low delay. BIER can meet these challenges faced by traditional multicast technologies. Its advantages are as follows. First, BIER allows the entire network to share one underlay network, without needing to establish an MDT for each multicast flow. Second, the underlay and overlay networks are deeply decoupled. If a fault occurs on the network, only IGP convergence is required, with multicast services unaware of the fault speeding up end-to-end service convergence. Third, BIER uses BGP to transmit the multicast group join requests of users to the ingress through only one hop. Now, let's discuss the definition of BIER. BIER is a bit index explicit replication technology. BIER defines a bit string, in which a bit position, numbered from right to left, is allocated for each ingress and egress. In the bit string, bit position 1 is allocated for ingress A, and bit positions 2, 3, 4, and 5 are allocated to egresses D, E, F, and G, respectively. Multicast messages are replicated and forwarded based on whether bit positions in the bit string are set. If a bit position is set to 1, the corresponding node has multicast traffic requirements, whereas if a bit position remains at 0, the node does not have these requirements. As shown in this figure, nodes D, E, and G have multicast traffic requirements. In this scenario, their bit positions are set to 1. Nodes A and F do not need to receive multicast traffic, and their bit positions remain at 0. And a bit string 10110 is then formed. Before node A forwards multicast messages, it encapsulates the bit string in their headers, based on which transit nodes replicate and forward the messages. Now, let's discuss some of the concepts that BIER involves. The first concept is domain, or BIER domain, which is a set of all BIER forwarding routers on a network. A domain can be divided into multiple subdomains, each identified with a subdomain ID. The second concept is bit forwarding router, or BFR. All nodes that support BIER forwarding are called BFRs. There are 3 types of BFRs. Bit forwarding ingress router, or BFIR, is a node that multicast traffic enters a BIER domain through and is referred to as an ingress BFIR. For example, node A in this figure. Bit forwarding egress router, or BFER, is a node that forwards multicast traffic out of a BIER domain. Nodes D, E, F, and G in the figure are BFERs. Transit BFRs are transit nodes that forward multicast traffic in a BIER subdomain. Nodes B and C in this figure are transit BFRs. The third concept is bit string length, or BSL. In this example, the BSL is 5. The fourth concept is BFR ID, which indicates the bit position in a bit string. In this example, the BFR ID of node A is 1, while those of nodes D, E, F, and G are 2, 3, 4, and 5, respectively. Transit nodes B and C do not need to be configured with BFR IDs because they only forward multicast traffic and do not need to receive multicast traffic. The fifth concept is BFR prefix, which is equivalent to a routing protocol's router ID and is used to identify a BIER node. In most cases, it is configured as a loopback interface's IP address. Next, let's discuss the BIER architecture. The BIER layered architecture decouples the underlay network from the overlay network. The BIER architecture consists of 3 layers. The bottom layer is the routing underlay, which is responsible for carrying BIER information to each site, BIER node. The intermediate layer is the BIER layer. After receiving BIER information from the routing underlay, the BIER layer calculates information about neighbors and the edge nodes that are reachable through each neighbor. Full mesh BIER networks are established through this process. The upper layer is the multicast flow overlay. After BIER tunnels are established at the BIER layer, the multicast flow overlay determines the tunnel to be used for multicast service transport. The routing underlay functions as a vehicle for transmitting and advertising information. The BIER layer is a computing layer that uses information obtained from the routing underlay to calculate BIER entries. The multicast flow overlay identifies the nodes that require multicast services and determines the BIER tunnel to be used. Next, let's use an example to describe how BIER entries are generated and messages are forwarded. As shown in the figure, node A is a BFIR, while nodes D, E, F, and G are BFERs. Nodes D, E, and G have multicast traffic requirements, and multicast services are transmitted through BIER. First, we assign BFR IDs to the BFIR and BFERs. We allocate BFR ID 1 to node A and BFR IDs 2, 3, 4, and 5 to nodes D, E, F, and G, respectively. Transit nodes B and C do not need BFR IDs. After the configuration is complete, the nodes flood their BFR IDs through IGP packets carrying a BIER TLV. This enables each BFR to learn BIER entry information and generate a BIER neighbor table. In the table, each neighbor has an entry, which is a set of information about edge nodes that are reachable through the neighbor. Next, let's discuss the BIER forwarding process, which varies according to the BFR node. For a BFIR, node A in this example, the forwarding process is as follows. First, node A uses an overlay protocol, BGP for example, to obtain a set of all BFERs with multicast traffic requirements. Second, node A encapsulates a BIER header for received multicast traffic. This BIER header contains a bit string that is a set of BFERs. In this example, the bit string is 10110. Third, node A searches its BIER neighbor table, replicates messages for each neighbor, updates the message copies by performing an AND operation between the original bit string and the one in the BIER neighbor table, and then sends the copies to the neighbors. After receiving the multicast messages with a BIER header from node A, transit nodes, nodes B and C in this example, parse the BIER header and perform an AND operation between the header and the ones and their neighbor entries. If the result of the AND operation is not all zeros, a copy of the BIER message is sent to the corresponding neighbor. If the result of the AND operation is all zeros, such as for node F, the BIER message is not replicated for the neighbor. After receiving the BIER messages, BIERs terminate the BIER process by decapsulating the BIER header, and then forward the messages through IP multicast. Now, let's focus on a typical BIER application scenario. NG MVPN over BIER is one such application scenario. Its implementation includes two parts. First is the establishment of BIER tunnels. Second is the generation of multicast VPN entries, which is similar to the process in P2MP MVPN scenarios, and is therefore not described here. Let's describe how BIER tunnels are generated in detail. In NG MVPN over BIER scenarios, the roles of devices vary according to the protocol perspective. From the VPN perspective, devices are classified into PEs and Ps. For example, nodes A, D, and F are PEs, whereas nodes B and C are Ps. From the multicast or service perspective, devices are divided into the ingress and leaf nodes. As shown in this figure, PEA is the multicast ingress, whereas PED and PEF are multicast leaf nodes. From the BIER perspective, devices are classified into 3 types of BFRs. PEA is a BFIR. PED and PEF are BFERs. PB and PC are transit BFRs. In this example, we use the multicast perspective and refer to devices as ingress and leaf nodes. Next, let's discuss how an NG MVPN over BIER tunnel is generated. When the tunnel type configured for NG MVPN is BIER, the ingress sends a BGP AD auto-discovery route, carrying PMSI tunnel information to leaf nodes. Upon receiving the route, each leaf node with corresponding group join requirements responds with a BGP AD leaf route. The BGP AD leaf route carries the BFR ID information of the leaf node and the related multicast group join information. After the BGP AD route exchanges between the ingress and leaf nodes complete, the mapping between multicast flows and all leaf nodes is established, and the set of the leaf nodes' BFR IDs, which is the bit string, is formed. That concludes BIER tunnel establishment. Now, let's discuss the forwarding process of NG MVPN over BIER. After receiving multicast messages, Ingress A encapsulates them with a BIER header and BGP VPN label. The BIER header contains 2 fields, BIER label and bit string. After encapsulation is complete, the ingress performs BIER forwarding. After receiving the multicast messages with the BIER header from Ingress A, Transit node B parses the BIER header, searches its BIER forwarding table, updates the BIER header, keeps the VPN label unchanged, re-encapsulates the messages, and forwards the messages through BIER. After receiving the multicast messages, leaf nodes PED and PEF parse the BIER header and discover that their bit positions in the bit string are set to 1. Then, PED and PEF locate the related VPN instance and search the multicast routing table of the VPN instance for an entry to forward the multicast messages to related receivers. That concludes the introduction to BIER. Thank you for watching.